Okay. Here we go. This is what it all comes down to. Fundamental theorem of calculus. I briefly talked about this last week. It's fundamental. It's a theorem, and it's the fundamental theorem of calculus. So there's two parts to it, and I kind of already gave you a little brief introduction to it. The first part is, again, here's what the whole idea is that derivatives and antiderivatives, again, antiderivatives, when I say antiderivative versus integral, I mean the same thing, okay? So when I take the integral of something, generally when I say antiderivative, I'm talking about the actual, like what's the antiderivative of cosine? It's sine, right? What's the derivative of sine? It's cosine. And then when I say evaluate the integral, right, I use the antiderivative to evaluate the integral. Does that make sense? Okay, so just like addition and subtraction. So again, it's a theorem, so we need to have a condition, and that's that it has to be continuous on a closed interval. Notice it doesn't say differentiable. So the only theorem, so we had extreme value theorem, intermediate value theorem, and mean value theorem so far. This is the fourth one, so there's four big ones. And you can abbreviate, so if we're justifying something, you could just say FTC for short. Fundamental Theorem of Calculus for abbreviation. So three of them just need continuous on a closed interval. That's the extreme value theorem needs continuity, intermediate value theorem, and fundamental theorem. What additional piece does the mean value theorem need? Continuous and differentiable. So this one doesn't have to be differentiable, because think about it, like if you had an absolute value with a corner, could you still find the area under that curve? Yeah, so we can evaluate the integral even if it's not differentiable. So we need it to be continuous. So let's say this is our function. So function is defined as the integral. What happens when we take the derivative of the integral? We get back what we started with, right? They're inverse functions. So now notice my lower limit of integration was a. A is just a constant in this case. The upper limit of integration had an x. And notice this was f of t dt, and it became f of x. So basically we're replacing whatever variable is here with the variable that we have at the top. So 1 over 1 plus t squared. So basically what I'm saying is I don't have to find the integral at all. The derivative of the integral is just going to give me back what I started with, but we're going to replace t with x. So in other words, there's no work to do. Nothing to do for these first two. Okay, next one. That's it. It's fundamental. What's the derivative of the integral of negative pi to x of cosine of t dt? Cosine x. How does that work exactly? Well, let's say we had to do this by hand. What's the antiderivative for cosine? Positive sign. Positive sign of t evaluated from negative pi to x, right? What? So if we were, let's say I'm not taking the derivative at all, and I said, oh, just evaluate this, what would this? So now what would happen? We would plug in sine of x minus sine of negative pi, right? But what would happen if I said, now take the derivative of that? What's the sign of, what would happen with this? It's 0, but it doesn't really matter Isn't this always just going to be a constant? Right? If I'm evaluating the lower limit at a constant, I'm going to get a constant. What's the derivative of sine? Cosine. Now, I didn't need to actually, so the whole point is you don't need to do all of this work, right? Because when I'm doing the derivative of the antiderivative, we can just go back to the integrand. Okay, does that make sense why that works? Okay, next one. Chain rule. What's wrong? Oh, sure.
I thought we were done with chain rule.
We good? Yeah. Okay. All right. So, chain rule, we use the chain rule when the upper limit of integration is not just x. So maybe it's an x squared, maybe it's a 2x. So what we're going to do is we will start off the same way. Now we have to make sure, we always want to make sure that the lower limit of integration is a constant. We'll look at some examples below where it's not. So we're still going to replace the t with the upper limit of integration. So that's going to be tangent of x squared times, now we want to take the derivative of x squared, which is 2x. So that's where the chain rule applies. And if you were to kind of think of this problem up here, like let's say that was an x squared, right? Do you see how if I had sine of x squared, I would, when I do the derivative, I'd get cosine x squared times 2x? And there's not really much we can do with this, so I'll just put the 2x in front. Okay. Now this time instead of t, I have a u, but it doesn't matter. We're still just going to replace. Oh, wait, sorry. Not equal. We're taking the derivative. So it's going to be negative 2x cubed minus 5, right? All times negative 2. So don't forget to multiply the whole thing by that derivative. Okay, we can simplify this a little bit, right? What's that? You mean the negative 2 all at the end? Oh, the negative 3 is irrelevant. So, because if I were to do this by hand, right, no matter what, at the end you would be evaluating it at negative 3. But when I do the derivative of that, it will always just go away. It'll become 0. So we don't really care what that lower limit of integration is, as long as it's a constant. Okay, let's see. This will give us negative 8x cubed, and then times negative 2 will be 16x cubed, and then plus 10. Okay, next one. So same thing, dy dx. Now we have variables in the lower limit of integration. Okay. What could we do with this one? Yeah. Okay, so if I just switched this to be negative 5 to x of 3t natural log of t dt, what happens when I do? I just replace all the x's, right? So I just have negative 3x natural log of x. I didn't have to apply the chain rule, which was nice. Okay, last one of these. So now the problem is I have an x and both the lower and the upper limits of integration. Any ideas? Okay, do you remember the additivity property where if you have two integrals that are basically right next to each other, you can make it equal to the whole thing? So what I'm going to do is I'm going to pick any constant, 2. It really doesn't matter, okay? You could pick anything. I probably wouldn't pick 0, though, just based on my function. I wouldn't want to evaluate natural log of 0, right? So just pick any constant. You can even just put like the letter A or letter C or something to represent. So here I have natural log of t dt, and then right, whatever that upper limit of integration. Yeah, that's a plus. And then 2 to x squared of natural log of t dt. So remember, like, Ben, you were asking on the homework, how could we assume that? It has to be true for any value as long as our function is defined. So I could have split this up. I could have put 10 here. I could have put pi here. It's not going to matter, because when we end up applying the fundamental theorem, right, those numbers become irrelevant, because if we do the derivative, that would just go to 0. Griffin?
Wait, I don't really get what we gained from doing that.
Okay, so we have to do one more switch around. I can't do the derivative of the integral without this lower limit of integration being a constant.
Okay.
So what I'm going to do is I'm going to separate it by introducing a constant and then flipping the first one. So we're good on this one. This one I don't have to change. This one I have to change to put the 2 on the bottom.
But then is it so?
So I'm going to make it negative.
Choose like a random number.
Yeah, yeah.
Good morning, Toledo. I hope you guys are having a great week so far. Today, we have a draw as far as the baby done from 320 to 335 in room 183. Tomorrow at lunch in the music room, we have our annual open mic. Today, during lunch, there is a sphere leader meeting in room 276. Please wish our boys soccer, far soft, JV, and varsity basketball teams good luck at their games today. And to quote a wise woman, I'd rather be dry, but at least I'm alive. Rain on me. Thank you so much, and I hope you guys have an amazing Tuesday.
That's so funny.
Okay. All right. Okay, does it make sense why I needed to do that? No.
I know why you have to flip it, but then does it still apply? It's not.
Okay, so in order to apply the fundamental theorem of calculus, I need to make sure that A is a constant and the upper limit of integration has the variable. So
why did we do that at all?
well, so we had a variable here and here, so I have to introduce a constant. Again, the constant that you choose doesn't really matter. Usually I pick 0, but do you understand why I didn't pick 0 in this case? Because you can't take natural. I also wouldn't pick a negative number, right? So I look at the function and I would pick a value just as long as it's defined. So I could have chosen 1. Okay, it doesn't really matter. And then I want to just flip the first one to make it negative. So now I have constants on the bottom for this and this part, and now I'll do each part separate.
But does the additivity theorem apply? Because
Yeah.
it's not...
No, it's okay. It's okay. This is the additivity property, and then this is switching the limits of integration. So it's kind of a 2-step process here. So we have to use additivity, introduce a constant, and then we have to flip just the first part in order to evaluate the fundamental theorem of calculus. Does that make?
Yes.
So 2 parts, additivity, then flipping. Okay. So we're going to have a negative square root of natural log of 2x times 2. So actually, are we okay if I just put the 2 in front? That's a negative 2. Are we okay on that first part? Plus, yeah, the 2 is the chain rule.
So it's not the constant, it's the chain rule.
Right, it's not the constant, it's the chain rule. Now we're going to have, I'll leave some space because I'll have chain rule again. Natural log under the square root of x squared times 2x. I'll just put the 2x in front. So when you have a variable in the top and the bottom, you're going to end up with 2 things added together. Okay? Are we all right with those? Okay. All right. Again, part 2, I didn't give it a name, but we've already done this. We did this on those worksheets. So part 2 says, what happens when I take the integral of the antiderivative? Okay, I get back, so here, let me remind you, if I take the integral of the derivative, I get back the original plus c. However, if I have limits of integration, right? So let's say this was evaluated from a to b. What's going on here? I can't. I know. Okay, hold on. Let's see if it'll start working. What happens if I do so this would be f of x evaluated from a to b. And that's how I get f of b minus f of a. Okay. I don't know why it keeps, I think it's when I do the screencast, like my things start happening weird. Oh, here we go. Oh, I did it. Okay. Yeah, I don't know if it's a new pen issue. Anyway, well, so here's what I was trying to write. So when we do the antiderivative of f prime of x, I get f of x evaluated from, so when we did these, when it was an indefinite integral, that's where we put the plus c. If we have limits of integration, we're going to evaluate from the top minus the bottom. So again, we've kind of already done these, so this is just good extra practice. We're just giving it a definition now. This is fundamental theorem of calculus part 2. Okay.
Do we have to memorize all of these? There's so many.
So you need to know the 4 theorems. Okay, and when we get to the test prep, even if you're not taking the test, we still need to do all the, is everybody taking? Not everybody's taking it? Yeah, seniors. I know all the juniors have to. Okay. But it was optional, but I think everybody is signed up. Okay. But there's only 4 theorems. You just need to know the 4. When we end up doing all the test preparation, we'll bring all 4 together and we'll put all the pieces together. It'll be okay. Don't worry. Okay. All right, what's the integral for 4? It's going to be 4x. 2x is going to be 2x squared over 2, so just x squared evaluated from 4 to 6. Okay. So let's plug in 6. Let's see, 24 plus 36, 60. I know, let's practice some of this because this could very easily, these are the types of problems that you wouldn't have a calculator for. And 16 plus 16, 32, 60 minus 32. 28. I know, it's easy to get 10 off, but let's... Okay, antiderivative for e to the x is e to the x Oops. And we want to evaluate it from -1 to e. So what do we get? E to the e minus e to the -1. What's e? Yeah, so e to the -1. I would just rewrite that as 1 over e. Okay. X cubed becomes x to the 4th over 4 plus x. Sorry. Evaluated from -1 to 3. Let's see. So we get, what's 3 to the 4th? Okay, thanks. 81 over 4 plus 3. And then we want to subtract -1 to the 4th, 1/4 plus -1, actually, yeah. Yeah, so don't overcomplicate things. A lot of times when we have fractions, it makes it easier just to evaluate those together. So 81/4 minus 1/4 will be 84, so which is 20. And then this would be 3 minus -1, so 3 plus 1. So 4, so 24. Yeah, Molly.
Kind of unrelated. For the, like, when we're doing these, but we put in ln, like the derivative, is that when x is at the bottom?
Yeah, it's only for 1 over x.
Really? 'Cause I feel like there was one on one of those 2 over x.
Oh, yeah, if it's 2 over x. Because if it were 2 over x, right, I could always move the 2 to the front.
Can you do that with any number then?
Yeah, as long as it's x to the 1st power in the denominator. So let's say it was the integral from 1 over x squared. That is not natural log.
Okay.
Because
So it's only when there's
because 1 over x squared would be x to the -2, and then I would do the power rule.
okay, got it.
Okay? All right. X to the 3/2, so let's see. So 5 over 2, so x to the 5/2 over 5/2, or multiplied by 2/5. Okay, so 2/5. Okay, so just a reminder with rational exponents, the bottom is the root and the top is like what you take it to the power. So we want square root of 4 to the 5th power minus plugging in 0.
Oh,
It would just be 0. So square root of 4 is 2. 2 to the 5th, 32. 32 times 2, 64 over. Maybe work on some of those multiplication and power rules. No, you're good. Okay, great. Again, when it comes to the trig functions, it's usually just on the unit circle. They're not like any crazy values here. Okay, negative sine of theta d theta. Okay. Well, what's the integral for sine? Negative cosine. So it would just be positive cosine of theta. Sorry, I know. The hardest part is just making sure you don't get those signs switched. Because, did you say negative or positive? Or were you answering positive would be the answer? Okay, sorry. Because I asked what the integral was of sine was negative cosine, and then with the negative it makes it positive. Okay, we're all on the same page then.
Yeah.
All right, so cosine of 5 pi over 6 minus cosine of pi over 6. Okay, it's got to be a 30-degree reference angle. We're talking quadrant 2. Good. Negative root 3 over 2 minus root 3 over 2, which will just be
Negative root 3.
Negative root 3? Well, you've got two of these, right? Right? This is negative 2 root 3 over 2. And then the 2's cancel.
It is cosine at the top because the derivative of cosine.
Yeah, remember how we check? If we do the derivative of cosine, we get negative sine.
So if it was sine, it would be negative.
Right, if this was just integral of sine, we would get negative cosine. Okay, all right. Next one. Okay, so we have to do something before we can integrate it. Yeah, we have to multiply that out, basically. So we have x squared plus 2x plus 1. Next chapter, we'll learn a way to integrate, kind of like backwards chain rule. So you see how this is really a composition of functions. We have x plus 1, and it's to the second power. But for right now, we'll just multiply it out and then just do the power rule. So what do we get for... So we got x cubed over 3 plus x squared plus x. Okay, well, plugging in 0 is easy, right? We'll just get 0. Just remember to put it, I usually just put it in as a reminder because we're subtracting, now plugging in negative 1 so we don't mess up any signs. So negative 1 to the third power, negative 1 over 3 plus negative 1 squared, so that's going to be 1 minus 1. So just 1/3 for the whole thing. Good. Okay. Are we good? Everybody got it? Okay. All right. So far when we did the integral, we were evaluating with area. Anytime it went below the x-axis, we made it a minus, right? So what if I wanted the entire region bounded by a graph and the x-axis? So in other words, I don't want to count the area that goes below the x-axis as a negative. How would we? So let's first, how would we express that? There's a few different ways we could think of it. So we're going to partition the integral, right? And look at it over each subinterval. Like we're going to count this as positive. We want this to be positive and this to be positive. So how would we set that up by hand? So first of all, what are these 2 points here? What are those zeros? Yeah, if I were to set 3x squared minus 3 equal to 0, divide by 3, right, we get x squared equals 1. So x would equal plus or minus 1. Okay, so the first part of the integral, right, that's already positive. So I'm going to put area equals. So I'm going to have from negative 2 to negative 1 of 3x squared minus 3 dx. Now the next part of the region goes from negative 1 to 1, but I'm going to subtract that area. And it's still the same function. So 3x squared minus 3, right? Because again, we're looking for the total area. So we just want to make sure any of those areas that are below, we make positive. Now, another way you could do this is you could just put a plus and then put absolute value around it. That would also be okay. So you could just find each integral and just make sure they're all positive areas. And then the last one is positive, and that's going to go from 1 to 2. Now, what do we know about these two areas here and here. They're going to be the same, right? Why? Because you have, it's symmetrical here. So if I find the area for this one, I can just count it for the last part, just to save some time. Yeah, Jake?
I don't understand why you're subtracting the middle thing if you said you want to find the area like that's.
Oh, so this area here, if I were just to evaluate the integral, this would end up being negative, but I want to count it as a positive. So another way you could do it, as I had mentioned, or you can make it plus and then put the whole integral part from -1 to 1 in absolute value. Right? So as long as you recognize any of the partitions that end up being negative, you just want to make it positive because we're looking for total area. Okay. We can do this pretty quickly. What's going to happen here? 3x cubed over 3, bless you. X cubed minus 3x. Now I'm going to do something, as I just mentioned. I'm just going to put a 2 in front. And you know what? I'm actually going to evaluate from 1 to 2 instead of negative. Okay. Remember how I had mentioned these two are the same area? So I'm just going to double the antiderivative, and I'm going to use 1 to 2 because it's easier to evaluate positive. You're less likely to mess up with positive numbers than negative. So there are some little shortcuts that I want you to recognize here. And then this one's going to end up being the same, x cubed minus 3x, evaluated from -1 to 1. Now, something we're also going to practice a little more. What do you notice here? This is symmetric with respect to x equals 0? Or y, yeah, y, the y-axis. I could double this area from 0 to 1, and that would also make it easier. Because isn't it easier? What happens when I plug in 0? You just get 0. Did that make sense? So I could make this a 2, and I could make this 0 to 1. It's a lot easier to evaluate that than from -1 to 1, because -1 to 1, that region is equivalent to 2 times the area from 0 to 1. Okay? All right, now we'll plug in. What do we get when we plug in 2? So that'll be what? Yeah, 8 minus 6, so 2. Minus, plug in 1. -2, so that'll make that plus 2. Minus 2. And what happens when I plug in 1 here? -2 again. Minus 0. So what do we get for the whole area? $12. Which one? The first 2 or this? There's lots of 2's in here. This one?
The one under.
This one.
On the other side. On the left. Yeah.
So I took this region and this region, and I doubled it.
I don't know, how did you get the 2 like in the brackets? Like, I don't understand.
You plugged in the bounds.
Oh, here. 2 cubed is 8, minus 3 times 2 is 6, so I got 2. Plug in 1, I got -2.
Okay.
Sorry, I just didn't, I skipped a bunch of steps. That's all. I just skipped steps. Okay, here's how we could do it on your graphing calculator. Okay, so I know all of that work, and you can just find the answer on your calculator. Of course, we don't always have our calculators, so how do we get to the integral sign again? There's 2 ways. You could go to menu and then calculus, or the shortcut is this button right next to the little catalog. Oh, I still have your calculator. I have it plugged into mine to try to figure it out. I think we'll have some time, so I'll try to watch. Do you guys see where the button is? So we want from -2 to 2. And how do we get absolute value? The same button. You can also go to menu and you can, but it's a lot easier to, these are like your little shortcuts here, right? And right above, I see the absolute value. So what that will do is what? It'll take anything that's below the x-axis and it will flip it to above the x-axis. So that little region of the graph, it'll just go above. And then we just type in 3x squared minus 3. Don't forget to put the end, the dx, 12. I know. The other way to do it is if you go you can type in also, if you graph it, right? So if you graph it, this is what I was talking about. It's going to take the graph and just flip that bottom part. And then you could go to menu. You could do analyze graph. You could do the integral. And we want from -2 to 2. Where do? Oh, it's hidden. Oh, it's gray. Oh, I see it. It's right here. It pops up there.
Yeah, can we just do it without graphing?
Yes, I was just showing you 2 different ways.
So, if there's like a problem like this on a test on a calculator,
If it's a calculator, okay, and I don't ask you, so often what I'll do is I'll say just show the setup and then use your calculator.
oh, so just write like the integral notation and then plug in.
Yep. Yeah. Sometimes I want you to justify it by hand. Okay. So we actually finished.